Our next speaker is Untitled from NPL, and he's going to talk to us about calibrating XPS intensity.
I'm from the National Physical Laboratory. And for those of you who are unaware of what that is, that's the UK National Measurement Institute. So we kind of care about whether the measurements are right or wrong, or what their accuracy is, or how you put a precision onto that, or an uncertainty. And for quite a number of years, there's been an activity in photoelectron spectroscopy. Martin Sear, Peter Compson, Steve has been there a long time, running all the instruments and collecting virtually all the data. And many years ago, the NPL provided the energies that you calibrate instruments to. So that's in an ISO standard. And they also provided a method for calibrating the XPS intensity scale. That isn't yet in an ISO standard. It did exist in some software that NPL produced back in the 90s. That software does not run on any modern computer. And we have the algorithm in a secret folder somewhere. But it's not freely available. Hopefully that will be remedied fairly shortly. Okay, so what I want to do, first of all, is take you through a few observations from interlaboratory studies. Now, NPL often runs VAMAS interlaboratory studies for XPS and SIMS and various other methods, so nanoparticle analysis and so forth. And they're intended to ensure that people around the world are making the same measurements and those measurements are comparable. And we've run a few of these, and I just wanted to go through a few of those observations, and talk a little bit about XPS quantification. So you can go to sleep during this because you know it all already. Some general instrument checks that you probably want to do before you do the calibration, and then calibration itself. And I just want to say you can use polyethylene as a reference material, and we've developed that quite recently. Okay, so this is a VAMAS study on organic compositions. Now this is actually, these are depth profiles, they're XPS depth profiles through a set of layered systems. There were, I think, 100 and, how many layers were there? 100 and something layers. But actually, it looks like there's 8 layers, but the layers that are 4, 5, and 6 are mixed, and they're mixed by doing sequential evaporations of sub-1 layer amounts of material, so we get the compositions that should be there. And this was intended primarily to work out how bad the matrix effect was in SIMS. And if you think you've got problems with quantification in XPS, you should try to do it with SIMS, because the matrix effects are rather extreme. But basically, we sent this out and we said, here are the pure layers, 1, 2, 3, most of 7 apart from a little delta layer, and most of 8. Can you tell us what the compositions of 4, 5, and 6 are? So that was basically the challenge we set the community. One of these contains nitrogen, and one of these contains fluorine. Now, if you want to get a degradation index out of this, you can see that as you go from layer 1 to 3 to 7, which are the pure layers, you have a degradation, and you have to take that into account if you're doing an accurate quantification. So these are the XPS results. I won't show you the SIMS results because nobody got it right. And we did at the end, after a lot of analysis, we worked out what the matrix effects are. But you can see that's pretty good. However, these were the results that we analysed at NPL based on the knowledge of what the pure materials were. They weren't based on somebody telling us what the percentage of nitrogen was and then trying to work out ab initio from the knowledge of the structures what the compositions were, because quite a lot of people got those numbers wrong. And this, I just wanted to quote myself on this, because I was probably being quite polite here. In some cases, it's clear that sensitivity factors used by participants were not correct or not correctly applied. It's not a significant source of error because we weren't using those in this analysis. But if we had, then there would have been a very significant source of error, by which I mean in some cases a factor of 2. So it was that bad. And also, when I finished that, I thought it was just sensitivity factors. I didn't really think about it much more than that. But I think actually it was a combination of two things. It was the wrong sensitivity factors and the wrong transmission function, possibly a combination of them both. So if we move on to a second one, we also ran a study on measuring shell thickness on nanoparticles. These were gold nanoparticles with a peptide shell. And this was very successful. It got quite a lot of participants from around the world, most people using XPS, some people using low energy ion scattering. Results are pretty good from that. Some people using medium energy ion scattering. These shells are much too thin for medium energy ion scattering. So we didn't get any useful results out of that. But at the end of it, when we got through, these are the XPS results. When they were analysed by a consistent procedure, we got 12% variability. So that tells you one thing that you should already know: XPS is trustworthy. But once again, these were not the results that were returned to us. These were the results that we got by analysing the data that was returned to us. So one of the biggest problems was we initially asked people to look at gold 4F intensities. Gold 4F is some distance from the other elements in the shell, the carbon, the nitrogen, and the oxygen. And it looks here like there's a lot of variation in gold intensity. But when you look at the gold 4D, what you find is there's not so much variation. So this variation has nothing to do with the amount of gold changing. It's to do with the transmission of electrons at those energies through the analyzer. And when you look at the results we got, this is basically the variation in what we call the equivalent homogeneous composition, the percentage of gold that was detected from the intensities. It ranged from less than 10% to about 30%. Now, if you did the calculations right on shell thickness, it should follow this line to translate into a thickness. Let's not talk about the way people did calculations. That wasn't very consistent either. So we got this huge range from less than a nanometer, and I haven't shown you the one that was about 50 nanometers because that just defies physics, to be honest. But I think that's just about guidance and having some tool to do the calculation. This thing here across the bottom, the percentage of gold, is something that we should have solved already. We shouldn't still be seeing exactly the same sample giving you such a wide compositional difference. We should have been getting, because the results were so consistent, and you see here, they should have all been clustered around this point here, not scattered around like this. Okay, so that's the transmission function that's uncorrected, and that gives, as you can see, that gives you a factor of 50% at least in uncertainty in the results that you're getting out. So it is important. You do have to pay some attention to it. So let's go through XPS 101. I hope you know all this already. If you don't, let me know and we can point you at some books. This is what you do when you calculate your do your quantification in XPS. You get your intensities from your various different peaks. Never choose the two peaks from the same element, otherwise you'll get the wrong composition. You'll get that twice. So you choose one peak from each element, divide it by a sensitivity factor, and then divide by the sum of that, and then you get an atomic fraction. You usually express that in atomic percent. And I like to call that the equivalent homogeneous atomic fraction, because that is what the composition would be if it was homogeneous in depth and all made of one particular phase of material. If it's neither of those, that won't be right, but that's what we all trust and hopefully understand. So what is this sensitivity factor? This sensitivity factor comes actually a lot of stuff from the sample, some stuff from physics, and some stuff from the instrument. So if you, like you did in the old days, and you mentioned an ES100 that went to Durham University, I did my PhD on that instrument. It was still working. Not in 1969, a little bit later on, yeah. But it was still just about hobbling on. more than 15 years old. I don't know how that happened. And what we did, we didn't have any of these transmission function things. So what we did is we just measured a load of compounds with different elements in. We knew the stoichiometry, and then we could work out what the sensitivity factor would be. But that would include all of these contributions: the instrument, the physics, and the sample. So the sample contributes something I've put as A. That's to do with elastic scattering mostly. And the part of the inelastic mean free path. So the inelastic mean free path varies with both with the energy of the electron, but also with the material. And then you have some physics. So that's the energy of the electron, part of the mean free path, the sensitivity, the photoionization cross section, some angular emission factor for each of the different subshells, and then the instrument is a transmission function and a detection efficiency. So all of these things are important. And what we hope to do when we apply a transmission function is compensate for all of this. And the idea is that you're using fixed analyzer transmission. So all the electrons hitting the detector are the same energy. So you shouldn't have a variation in the detection efficiency with different energies. So basically you're getting the transmission function and correcting for that. And then you're just left with the physics. And you hope that the sample stuff doesn't really matter that much. And that's what you do when you do a quantification. And the sample stuff honestly doesn't really matter that much. The physics bit does. Okay, so what is the transmission function? The transmission function is the efficiency of an electron going from here all the way turny round in a magnetic lens, up through a slit, up through another slit, all the way through, down through a couple of other slits down this end, and hitting the detector on the far side. And the efficiency is pretty good if you're right in the middle. As you go off to the side, it gets worse because the angular collection goes down. And if there's any slits in the way, that could change the way that the electrons go through. If your focusing isn't perfect, then that will change with the energy and so on. How am I doing for time, by the way? I'm trying to stretch this out because I know you're behind time.
No, you're good.
Okay. Because I can go even slower. So
15 minutes.
So if you want lots of counts, then you want to have all those lenses in operation, which means there's all kinds of things that might go wrong in this analyzer in terms of the efficiency. So to calibrate it, what you do is you have some true spectra that are accurate spectra of the material, looking at the reference material. You find out what spectrum you get from those, and you then take that spectra you've got, divide it by the true spectra, and that's your efficiency or your transmission function. I think technically it's the instrument energy response function, but everyone calls it transmission function. There's a couple of things to just note, and these came out of an interlaboratory study that we ran on transmission functions. The first is you've got to watch out for dark noise, particularly if you're using polyethylene to calibrate it. There's not many counts coming off polyethylene, so if you have any dark noise, that contributes to things at the low count rate areas. And this instrument here, very interestingly, this is dark noise, and this is the kinetic energy, and there's a correlation between the two. So there's something wrong with that instrument. So always have a quick check, make sure your dark noise isn't too high. You might, I don't know, do you have an equivalent of a discriminator these days? Can someone tweak that up a bit? An engineer, call up Kratos, please change my discriminator setting. Yeah.
Software, rather than pop. That's dark noise with the X-ray on.
Yeah, so that's with no sample in. Actually, the same thing happened with the X-rays off for this particular instrument. It's not a Kratos instrument, don't worry.
Everyone get that online.
The other thing to look out for is internal scattering. So all analyzers scatter things internally. And we did find some instruments had some significant internal scattering. Others were fairly good and didn't have much that was detectable. And the other thing to be aware of is analyzer warm-up. It will take about half an hour for your instrument to get warm enough to give you a constant performance. So if you turn it on, do your transmission functions, then by the time you get from the start to the end of the spectra, the whole thing's changed because the whole thing's warming up while you're doing the measurement. And the same if you want to do careful analytical work, warm the instrument up before you start. Okay, so the other thing that you should be particularly careful of, particularly if you're calibrating an instrument, is saturating the detector. So these really efficient instruments that we've now got that can really collect all the electrons and throw them onto the detector, they're quite capable, even in routine operation, of completely swamping the detector and making it nonlinear. So this is a new version of the NPL calibration software. It's a lot faster and easier to use than the old one. Steve will tell you. So there's what you do is you put copper, silver, and gold in. Now these ones here, there's a slight problem. You can see that when you calculate the transmission function, silver and gold look good. That's the blue and the red dots, but the copper's looking pretty bad. And the copper, if you look at this, so this uses the background intensity, not the peak intensity. And you can see the copper spectra is getting up towards 500,000 counts, and these ones are a bit lower. So that's what happens if you get rid of the copper. You go from about 7% uncertainty in your XPS measurement to a less than 3% uncertainty. That's now agreeing. And the changes are the transmission's a bit higher here than you'd predict up with this set of data, and a bit lower than you predict there. But it also means that basically anything above that line is suspect. That's where the saturation is happening. Above about 250, 300,000 counts per second on this instrument. That's all your peaks. And you do your quantification on your peaks. So be aware that sometimes you've got a really intense peak. You can't really trust the counts in it because you're into a completely non-linear regime. I suspect actually there's always a lot of fuss made about PTFE and why that doesn't quantify quite right. That's probably because the fluorine 1s intensity is shooting up there into the non-linear regime, or at least one of the reasons. Because it never seems to be consistent. Either it's too high or it's too low, and all the rest. Okay, so here's just some examples of transmission functions from an Axis Ultra. This is the NPL instrument. See the hybrid and the electrostatic. These are typical functions, and they all come down with kinetic energy. So dropping by a factor of about 2 from one side to the other. Now this is an observation I think that Vincent Fernandez has made, amongst others, is that if you've got a well set up imaging mode, what you're doing is you're projecting a constant area from the sample onto the detector. And as long as the angular acceptance remains the same, but everything else is well set up, that means if you're in your field of view modes, you should have a flat transmission. So it should be the same efficiency across the board. That doesn't mean to say that your detector is constantly efficient across from one side of the detector to the other. That's something you need to work out. But at least the transmission is constant. But it has to be well set up. Sometimes it isn't, or it drifts. So these are just some samples. I'm looking for beta testers for an online version of the XPS calibration. I know some people participated before in a previous attempt to do this. This time we have our digital products team on board, so it's a bit more professional. So if you want to join us in that study, please let us know. All we want you to do is be able to spot a copper, silver, and gold, and take some spectra without saturating your detector. And we'll see whether this is going to be a useful thing for the community or not. Okay, so the other thing we've done recently, this is really thanks to Ben Reed at NPL, is to look at other reference materials. Not everybody has an ion beam, so not everybody can sputter their copper, silver and gold and get a useful reference spectra. So one of the things we looked at is, can we use a polymer as a reference material? Because effectively, all you need is a material that you can prepare, clean, take the spectra of it, and compare to a known true spectra. And because we're using backgrounds, it's actually probably a good idea to have a spectrum of a material that doesn't have too many peaks in it. Polyethylene is pretty good. It's got carbon, so you've got the valence band, the carbon 1s, and you've got the Auger, KLL Auger. So that's pretty simple spectra. The only downside is there aren't many counts between the C1s and the valence band, so you have to spend a lot longer counting there to get the statistics. We had 44 participants to find out if this was viable. Okay, so we did all of this, and the conclusions were you can use polyethylene. There are 2 papers out. It's in JVSTA. One tells you how to calculate a reference spectra for polyethylene using a mathematical function. So you don't need to transfer data. It's just maths. There's just a couple of lines that you need. And then the procedure on how to do it, and the actual study itself was published as well. So these are in a set of guides that Don Bayer organised that are now published as a separate journal. I think they were released as a separate booklet on reproducibility in X-ray photoelectron spectroscopy. So the conclusions are that you can do it. The transmission functions are about good to an accuracy of 4 or 5%. That's not as good as the copper, silver and gold method, but it still works to for those people who can't access the methods for calibrating their spectrometer. And we're putting this forward as an ISO standard that's in progress at the moment. So it's out for comments in the first round. So just here are some examples to prove that you get, this is the polyethylene, not a lot of peaks, that's good. And these are the transmission functions that came out. You can see the variety of transmission functions out there, including those with a little bump in the middle. And this is what you get using gold, and you get pretty much the same result. It may be a slight factor difference, but that's not so important in quantification. So what I've done, I hope I've convinced you need to think a little bit about intensity calibration. And I know that Kratos have thought about it, and I know they have something for their silver anode, which is consistent with their aluminium anode. You can use polyethylene as a reference material, so that's public now and openly available. Easy to clean ex situ, get a metal scalpel. Not, as I originally told Vincent, a razor blade, because razor blades come coated with PTFE, so scrape it as much as you like, all you see is the fluorine. There's no requirement for ion beam sputtering unless you've got a really dirty instrument, and then you might as well clean your instrument. And the uncertainty is pretty good. You can get to within 4%. And if you've got any comments or have any questions about that, please contact either myself or Ben Reed at NPL. And this is a big thanks to everybody who participated in that study, including the good folk of Kratos. And thank you for your attention.